So we're going to start talking about three-dimensional vectors, and this is actually one of the largest topics that we're going to be talking about throughout this course, because vectors are going to govern vector value functions, which we're going to talk about later in the course, as well as vector fields. So we probably remember from physics or even a pre-calculus course that vectors are entities that are comprised of a magnitude and direction, right? So let's just make sure we have that fundamental definition. Is a vector is some sort of entity with both a magnitude and a direction. All right, and we have these standard forms also in a vector v from the origin. Okay, so a standard form is just basically a vector that's been transposed from the origin and has the form v is v1, v2, v3. We have the hard brackets. You may have seen a vector v written like this in other classes too, and that's perfectly fine too. Zero vector is just a vector that has no direction, no magnitude, and we could write the zero vector like that as well. We have standard unit vectors, and the standard unit vectors are in the x direction, the y direction, and the z direction, and they have a magnitude of 1, and they fall right along the x, y, and z axes. And then we have this other form, so we have a standard form, and then we have a component form. Sometimes this is called a linear combination. So if I use those terms interchangeably, make sure we understand the difference between standard and linear combination. It's really easy to compute a vector and put it into the standard form or even to the linear combination form. And we just take the initial and subtract that from the terminal point. And we just put that into a vector form. There are some properties of vectors that we're going to be looking at. Two vectors are equal if and only if their individual components are equal to one another. So u1 is equal to v1, u2 equals v2, u3 equals v3, excuse me. We again, to be able to figure out a vector v given the initial and terminal points, terminal minus initial, the length, otherwise called the magnitude. All right, most of the time when I talk about this, I'm going to define that as the magnitude of the vector, and that's just going to be, if it's in the standard form, each of the individual components squared and then the square root of that. A unit vector in the direction of any vector is going to be equal to the vector v divided by the magnitude of v. And a unit vector is special because it always has magnitude of 1. So that's going to be important about the unit vector. If you want to add two vectors, you just add the components. Same thing with subtraction. And then if you want to do a scalar multiplication or perform a scalar multiplication, you just take that scalar and you multiply it. And essentially what a scalar does, it just increases the magnitude. So let's say we have a vector v that looks like this. And if I wanted 2v, then that would just double the size of that vector. Notice that they have the same direction. All right, so that's all that does, is it just doubles. Or even if I wanted to take half of v, then it would be in the exact same direction. It would just be half of the initial magnitude of that vector. All right, so nice and easy when we're doing that. And then finally, two vectors are parallel if for some reason there's a scalar that we can multiply one of the vectors by to get to the other vector. All right, sometimes that's called linear dependence for any of you that have suffered through linear algebra at this point. Right. So let's just take a look at a couple examples of being able to work with vectors. All right, and you'll see that it's really easy because all you have to do is just know the basic four fundamental operations: add, subtract, multiply, and divide. All right, so consider u and v. All right, u and v are these vectors. All right, so they're both in no form whatsoever, not a linear combination, nor is it in a standard form. And so we want to write both of them in standard and component form. All right, and again, we want to make sure for the component form we understand that's linear combination. We're going to find the magnitude. We're going to find a vector of magnitude 3 in the same direction of u, a vector of magnitude 3 in the opposite direction, and then we're going to do a couple operations for u minus 3v. Right, so vector u is going to be equal to terminal minus initial. All right, so this is the terminal point and this is the initial point. So we're just going to say that's going to be 2 minus 4, comma, 4 minus 2, and then 3 minus 1. All right, otherwise known as negative 2, 2, 2. All right, and that's in the standard form, which is the same as minus 2i plus 2j plus 2k. All right. And again, if you've seen this before, that's another notation for a vector if you put a hat on it. So this is the same thing as I with an arrow over top of it. All right. If I want to go through and find v in what v is going to be equal to in both standard form as well as a linear combination, v is going to be equal to, this is our terminal, this is our initial point, so 2 minus 2, 3 minus 3, 4 minus 0, or 0, 0, 4, or another way to write that is going to be 4k. So we'll keep that in mind that the zeros are implicit. Another way to write it if we really chose to would be 0i plus 0j plus 4k. All right, but usually we just write it as the 4k form. All right, so not too bad. All right. If I want to find the magnitude of each of the vectors, so I'm going to find magnitude of u. That's going to be equal to the square root of negative 2 squared plus 2 squared plus 2 squared. That's root 12, right? Because we would have 4 plus 4 plus 4. Or, since 12 is 4 times 3, we could write that as 2 roots of 3. Now the magnitude of v is actually a lot easier, all right? And you might already know that this is going to be 4 because there is nothing in the I and the j direction or the x and the y direction. We're just going 4 units up in the z direction. But just to verify that, the magnitude of v is going to be equal to the square root of 0 square plus 0 square plus 4 square, which is going to be the square root of 16, otherwise known as 4. All right, so this is letter A and B, and this is letter A, and this is letter B. All right. So now we're tasked with being able to find a unit vector in the same direction as u, but it's going to have a magnitude of 3. And then we're also tasked with being able to find a vector in the opposite direction of u. All right, and both of these are fairly easy. Now recall that to find a unit vector in the same direction, that's going to be equal to u divided by the magnitude of u. Okay? Or, in other words, that's going to be 2 root of 3, or 1 over 2 roots of 3, excuse me, times negative 2, 2, 2. Or in other words, if we were to distribute that through, remember, if we have a scalar we can just distribute through, that's going to be equal to negative 1 over root 3, 1 over root 3, 1 over root 3, because the 2's would cancel out. Now this vector is a unit vector, which means that it has a magnitude of 1. But we want one that has a magnitude of 3. So all we're going to do is we're just going to multiply this by 3. and we can just keep the 3 on the outside. We don't have to distribute it through. All right, so this is a vector in the same direction that has a magnitude of 3 of u. Just as easy to get a vector in the opposite direction. We're just going to multiply by negative 3. All right, so this has a magnitude of 3 in the opposite direction of u. All right, so same direction, just multiply by the scalar once you find a unit vector. Opposite direction, multiply by the opposite of that scalar times magnitude or times the unit vector of u. All right. Last two things we have to do, we just have to do two operations, 4u minus 3v, and then u plus 2v. All right, so I'm going to make some room here so we can compute those. And let's just recall what u and v were. All right, so u was negative 2, 2, 2. And then v was the vector 0, 0, 4. All right, so all we're going to do at this point is we're just going to go ahead and take 4u minus 3v. So 4 times negative 2, 2, 2 minus 3 times 0, 0, 4. All right, and if we compute that, we have negative 8 minus 0, which is negative 8. We have 8 minus 0, which is 8. And then we have 8 minus 12, which is negative 4. All right, so again, all we did to get that was multiply through on both, and then just combine the terms. Okay, so for the first one, we have 4 times negative 2 is negative 8, and then we have negative 3 times 0, which is 0, and we just add those together. All right, so nice and easy for that. Now the last thing that we have to do is we're asked to compute u plus 2v and then find the magnitude. All right, so u, again, was negative 2, 2, 2. 2v is 2 times 0, 0, 4. All right, so u plus 2v, if I was to compute that, so u plus 2v is going to be equal to negative 2, 2, 10. Right? And again, we just take the 2 times 4 is going to give us 8, and then 8 plus 2 is going to give us that 10. If we want to find the magnitude of u plus 2v, then that's going to be equal to the square root of negative 2 squared plus 2 squared plus 10 squared, which is going to be equal to root 108. 108, I believe, is going to be 36 times 3. Yeah, that's 108. So this could be written as 6 roots of 3 if we really chose to. Okay. All right, so hopefully this gives you a good basic introduction of vectors in 3 dimensions. The last set of videos, or the last video that we're going to look at in this section, just goes through a little bit of an extension with some of the applications of these vectors in 3 dimensions.